Okay, but like stop you don't.
All right, here we go, guys. Here we go. If I get your attention up here, please. So, and by the way, I'm videoing this so that way people that are gone can kind of follow along with what we did. Okay. So what we did was we cut a square out of each corner of a piece of paper. Okay. We cut a square out of each corner of the piece of paper. Then we folded up the sides to create an open-topped box that looks something like this. I had everybody do different sized squares out of the corners, so then we would create a bunch of different sized boxes. Here are some of the results. If you cut a 1-inch square out of each corner, you end up getting a volume of 58.5 inches cubed. And then you can see all the other results based on the different size squares that some people chose to cut out of the corners of their pieces of paper. If our goal was to get the largest volume box possible, the highest that we got so far that I've seen is this one, where we cut out a 1.25-inch square out of each corner, and the volume was 63.75. Here's my question to you. Do you think you can get a box that has a larger volume than this? Yeah? Share your ideas. How much? 1.5? Why do you think 1.5? I don't disagree, it's a good guess, but why do you guess that? What are you seeing that makes you guess that?
Oh, 2 is less than that one, so there's got to be somewhere in the middle where it like switches, where like it'll start curving back and forth. How big you get.
Okay, so you're noticing that at 2 inches, when we cut a 2-inch square out, this was our volume here. Now as we go larger than 2, what's happening to the volume? It's getting smaller. But at 1 inch, it was this. At 1.25, it was this. So it's kind of growing from 1 to 1.25. So we're thinking, as we move from 1.25 towards 2, it's probably going to reach its top and then come back down as far as volume is concerned. Okay? You might enjoy this, especially those of you that make perfect boxes and tape up the corners and everything else. Not that anybody would do that. All right? If you wanted to, you could sit here and mess around for a while and try to figure out what the biggest box is, right? Okay? Or, instead of doing this over and over and over again, the goal of this activity is to come up with a polynomial or an equation that represents the volume of the box. And then therefore find how we could make the largest box possible given that amount of material to begin with. You guys follow me? So that's going to be our goal. We want to figure out how to get that largest box possible using a mathematical equation. So, if you think about it, you had an 8.5 by 11 sheet of paper. Then you cut square corners out that were different lengths depending on who did what at your table, right? So that's our variable. That's what we don't, that's what we can change. That's what we can adjust. After you cut out those squares, to find the volume, you will take the length times the width times the height. Okay, here's the algebra part that I want you to all know. Okay? If our original length was 8.5, after you made your cuts of X units, how long is it? Now, how long is it? 8.5 minus 2x. Because it was 8.5, everybody's watching, it was 8.5, and I took x off of that side, and I took x off of that side, so now I have 8.5 minus 2x. How wide is it? 11 minus 2x, because it was 11. We took a little x piece off of this side. We took an x piece off of this side. So now you're 11 minus 2x. And how tall is it? X. Because however tall it was, when you folded it up, the length that you cut out is your x.
That's how I.
So volume equals 8.5 minus 2x times 11 minus 2x times x. Do a little distributing. I'm going to need a little bit, maybe I won't. 8.5 times 11, that'd be 88 plus 5.5, so 93.5. 8.5 times negative 2, that'd be minus 20x, minus 22x, plus 4x squared. All that times x. I'm going to work backwards here. 4x cubed. Combine my like term, that's negative 42x times the x, so minus 42x squared plus 93.5x.
I remember doing this last year.
Okay? So here's my volume equation. Here's my volume equation for the box that you see in front of you. We want to know what value of x makes volume the biggest number possible. Okay, and that's essentially what you guys were doing, is you were trying different size x's to see how large a volume you could get. Now that you have a formula, you could try plugging in different numbers into that formula and see if you can get the largest value possible for volume. Or, somebody just said it, we could graph it
Who says that?
and find the largest volume possible.
Martin guy.
Come on. You guys watching this still? Might want to. This will be a test question. 4x to the third minus 42x squared plus 93.5x. All right. Well, look at this. Looks like I got some sort of vertical almost here, and then like this here, and then like this here. Kind of hard to see that graph. I'm going to adjust the window because I know what these things represent, right? X represents what? The size of the cut, right? Isn't X the size of the cut? Okay? I don't need to see negative cuts, so I'll go 0, and I definitely don't think I can cut much more than 6, right? I mean, I couldn't cut 6 out of each side. I only had 8.5 to begin with, so 6 is plenty. Y-axis, I don't need to see negative, so I'll start at 0. But Y represents my volume, so that could be a pretty big number. Should we go 80? Okay.
Oh, there.
So,
Oh.
if you look, what I've done here is I've kind of found a portion of the graph that makes some sense. And where on this graph am I going to look to find what the maximum volume could be? Right up at the top, right? Okay? So if I click up there, that way those of you can see that are watching. When you click on Desmos towards the top of a graph, it will identify where that maximum value occurs. I click on that coordinate and I see 1.3885, comma 59.559. What does that mean? The X value,
That's how big your cut is.
that's how big of the cut you should have made
And then that's the total.
in order to get the
Total volume.
biggest volume possible. Okay? Now, did I
Yeah.
make an error in my math because we got higher volumes?
Yeah.
I may have. Where's my error? Anybody catch it?
Right there.
8.5 by 11 is how much?
93.5.
Okay, so that's fine. Let's find the error. What's 8.5 by 2?
7.
17.
Yeah, 17.
You said 20.
You put 20, 17.
Oh, yep. So then let's go
22 is still right, yeah.
22 still right.
Negative 39.
So 39. Awesome. Thank you. Now I think we feel better.
There it is.
Now it's looking like maybe that's probably correct based on some of our other calculations we made. So it looks to me like if we cut out a 1.58-ish inch square, we can get a maximum volume of 66.148. Okay? And we found that by creating an algebraic expression called a polynomial. And then we graphed that polynomial and figured out where it hit the maximum value. Okay? In this course, you'll get to use Desmos to find this. In calculus, you could do this without graphing. Okay? Once you learn calculus, you learn how to find the maximums and minimums of certain functions without having to graph it by doing derivatives and setting those equal to 0 and so on, which is something you won't do for a couple of years yet. But you'll be able to do all this without a graphing device. Okay? You'll be able to use Desmos, and I expect you to be able to know how to. All right? This would be the work I would really look for in your problem. Honestly, I'll tell you this: if you're going for speed, though, it probably would have been just quicker to type this in right here, because this is the same thing as this. This is in factored form. This is multiplied out, and I actually made an error when I multiplied it out, so it caused me to be wrong. Had I entered this, I wouldn't have made the error. You follow me? Okay. So that's just. But at least when you show me this, you are showing me you know how to find volume of the box and you're using the original dimensions correctly. All right? But this graph ends up becoming what's called a polynomial. This would be a cubic polynomial because the highest power is x to the third. That's called a cubic polynomial. And we'll get into what they're called here this week. Okay? The graph itself ends up looking like this. Okay? However, why was this part of the graph irrelevant? Can't make negative size cuts and you can't have negative volume. Why? These are good test questions, by the way. Why from here to here, between my hands, why is that irrelevant?
Once again, negative cuts or negative.
I'm going to correct. He said you can't have negative cuts or negative volume. I'm going to disagree with half of that. Aren't these positive x values right here? These are positive x values, so that would be a positive amount of cut. But what can you not have? You can't have a negative volume, right? The y values are below 0. So why does this not make sense right here in the context of our story problem? You can't have negative volume. Okay? So now, all this over here. This would be a positive cut. This would be a positive volume. Why does it still not make sense?
Because it's big enough.
Paper's not big enough, right? You can't cut a 6.8-inch square out of each corner because you'd run out of paper. So, what domain is feasible? What domain is really the only part, what x values are really the only part that makes sense to us? 0 to 4.25. We're really only concerned with this part of the graph. This part doesn't make sense, okay? This part doesn't make sense, and that part doesn't make sense. So we're really only concerned with this part right here. All of these coordinates would represent different sized cuts that you could make and the volumes that correspond. So some of you made a 1-inch cut, right? Those of you that made a 1-inch cut, was your volume 58.5? What else did we have? We had a 2.5-inch cut, didn't we? So 2.5, 52.5. All these coordinates on the graph would represent all the different possibilities for the cut, size of cut that you could make and the volume that corresponds to it. But if you want to know the maximum, you click right there on the maximum on the top. Okay? Obviously, you wouldn't have volume if you didn't make a cut, or if you made a 4.25-inch cut, you'd have no volume because you couldn't fold it up and make the box. All right? Okay, so the goal of today was to really just introduce you to how polynomials can be used to solve different types of problems. We're going to really dig into what polynomials are over the next couple of days. We'll get in more just kind of common examples, working through some simple problems. Okay, but I thought this was a good activity, got you doing something, and you can see a purpose for polynomials. All right?